Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL TA for the course Introduction to Probability Theory and Statistics. This course is offered by Professor S. Dharmaraj. He is a professor in IIT Delhi. This is the 6th week of a 12-week course. So up to last 5 weeks, we have discussed about several things related to the probability theory, like basics of probability, in which we will discuss about the definitions of probability, sigma field or sigma algebra, and Bayes theorem, conditional probability. Then we will discuss about random variables, in which we have discussed about discrete and continuous random variables, a mixed kind of random variables, the properties of random variables, etc. In third week, we have discussed about moments and moments inequalities. We will discuss about the different kinds of moments and generating functions like moment generating function, probability generating function, characteristics function, etc. In the fourth week, we have discussed about like some standard discrete and continuous distributions. Standard discrete and continuous distribution. Like for discrete, we have discussed about Bernoulli, binomial distribution, Poisson distribution, geometric distribution, negative binomial distributions, and the properties and their moments. Also, we have discussed about the continuous distributions, in which like normal distribution, gamma distribution, beta distribution, Weibull distribution, and the properties of these distributions. In the last week, we have discussed about some higher dimensional distributions or multivariate distributions, like higher dimensional distributions, like up to in fourth week, we have discussed about univariate distribution when we have only one random variables. But in the in the fifth week, we have discussed about when we deal with more than two or more than one random variables. So that are called bivariate random variables or multivariate random variables, and those distributions are called multivariate distributions. Okay, we have used we have discussed about different marginal probabilities, how to calculate the marginal probabilities from the bivariate or joint probability distributions. Now in week 6, we we will discuss some functions of several random variables. Okay. Functions of several random variables. Several random variables in which we will discuss about distributions of functions of several random variables. Distributions of functions of several random variables. Some important results related to these distributions. More important results related to these distributions. Then we will discuss about ordered statistics. Which is also a function of a special kind of functions of several random variables. And then we will discuss about conditional distributions. And at last, we'll discuss about some random sum. Okay, these are actually use. Suppose we have more than one or more than two random variables, and then we need to transform those random variables in some other kind of random variables. Then these topics, these concepts are used. Okay, so we will discuss these concepts in sixth week lecture. Okay, so let's start with the distributions of functions of random variables. Okay. Uh, Suppose like we have a different kinds of different random variables. Suppose x1, x2 up to xn. Suppose we have a sequence of random variables x1, x2 up to xn. We have some known information regarding these random variables. Okay, these are known random variables, and then we transform these random variables in like y1, y2 up to, suppose we have considered yk random variables. Okay, so our aim is to like where y is like defined with respect to x only. Like suppose the random variable y1 is defined as g1 of x1, x2 up to xn. In a similar manner, y2 is defined like g2 function x1, x2, xn. And in a similar manner, y sorry yk, the random variable yk is defined with the help of random variables x1, x2, xn. We have now k transformed random variables, which is depend on x1, x2 up to xn random variables. Okay, so here gi is actually are Borel measurable functions. We have discussed in the fifth week, like when these y variable is associated with x variable via via a function, and those functions are Borel measurable, then those y variables are also random variables. Okay, that we have already discussed in the previous lectures. So in that case, we transform the random variables with the help of known random variables. Okay. Now, for example, suppose 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 x1, x2 up to xn are discrete kind of random variable, discrete time random variables, and then we can define the joint PDF of y. When we know about the distribution of x, then we define the joint PDF of y. This can be defined with the help of the distribution of x only. Okay, and this is defined as like probability, since y1 is nothing but g1 of x1, x2 up to xn. It is a function of x1, x2 up to x1. Okay, so we can replace y with g1 of x1, x2, xn, which is equal to small y1. In a similar manner, y2 can be replaced by g2 of x1, x2, xn equal to y2. In a similar manner, we can define gk of x1, x2, xn, which is equal to yk. Okay, this is how we associate these different random variables. Okay, now to find the PDF, find the distribution, we can write it like this: summation, which is equal to summation probability that x1 equal to x1, x2 equal to x2. These are only notation how to write. Okay, and xn equal to small xn. Okay, under the condition, what are those conditions are like? The first one is x1, x2, xn are the n tuples. Okay, belongs to Rn. Okay, n dimensional random variables are these. So Rn, and also this condition must satisfy. So we should also write there like g1 of x1, x2, xn equal to y1, g2 of x1, x2, xn equal to y2, and gk of x1, x2, x1 equal to yk. When these two conditions are satisfied, then we can we are able to find the distribution of y when we know the distribution of x. Okay, this is the general formula actually. We can discuss it via some example. Like the example one, suppose we have a two-dimensional or bivariate random variable. So let x1, x2 be a two-dimensional discrete type random variables with the following joint PMF, joint probability mass functions. We are given the different joint probability mass function like x1, x2. Okay, suppose the value of x2 either 0 or 1, and for x1 it is either -1 or 0 or 1. Okay, so the distribution of probability is like 1 by 7, 2 by 7, 1 by 7. It's 1 by 7, 1 by 7, 1 by 7. So if you see, you will find the sum is 1. So we can say that it is a valid two-dimensional discrete probability distribution function, probability mass function, I mean. Okay, so now we need to find a transformed variable, the distribution of a transformed variable, which is associated with the variable x1 and x2 only. Okay, so let's define here only. Let's define a random variable y1, which is defined via g1 of x1, x2, and the functional form is like x1 plus x2. Okay, and also y2, which is g2 of x1, x2, and this is defined as the product of the two random variables. Okay, so we have a joint PMF of x1, x2 random variables, and the distribution is given in the table. Now we need to find the joint PMF, joint probability mass function of y1 and y2 variable. Okay. And the y1 and y2 variable are associated with x1 and x2 variable in the following manner. Okay. So our aim is to find the joint probability mass function of y1, y2 discrete random variable. Okay. So this is how the question is framed. Okay. Now we need to solve. Okay. So here you can see that the range of x1 is -1, 0, and 1, and the range of x2 is 0 and 1. And y1 and y2 is defined as summation and product of x1 and x2. So let me write, since x1 takes values -1, 0, and 1, and x2 takes value 0 and 1. Okay. So on that basis, y1 has either -1 value, y1 has either 0, y1 has either 1, or y1 and either 2. So there are these four possible values of y when we are given x1 and x2 equal to this. And how? Let's write here. Okay. So for example, here we have like ordered form of for y1. So suppose this is the case, x1 equal to -1, x2 equal to 0. In that case, the value of y1 is defined as x1 plus x2. Okay, so -1 it comes out to be 0 when it is either -1, +1, or 0, 0. Okay, there are only 8 possibilities now: x1, 3, and 2. Okay, so then y1 equal to 1 comes out to be when it is either 0, 1, or it is either 1, 0, and 2 comes out when the value of x1 and x2 equal to 1, 1. Okay. The, in a similar manner, the value of y2 have either -1, y2 have either 0, and y2 have either 1. Okay. Now, the value of y2 is defined as the product of x1, x2. The product comes out to be -1 when the value of x1 and x2 is -1 and +1 only. Then the value of y2 comes out to be -1. It comes out to be 0 when one of the x1 or x2 value is 0. So -1, 0, 0, 0, 0, 1, and 1, 0. These are the four possibilities of x1 and x2 when the product gives 0, and it gives 1 when it is 1 and 1. Okay, so this is how x1, x2 related to the y1 and y2. Now we need to formulate the table for the joint probability distribution of y1, y2. So let's suppose we have y1 and y2. So y2 has values -1, 0, and +1, and y1 have values like -1, 0, +1, and +2. Okay, so y1 and y2 comes out to be -1. Okay, here you see that y1 equal to -1, y2 equal to -1 when it comes out to be either this or this. There is nothing common in between them. No? So it comes out to be the probability is 0. Okay. Again, we take y1 equal to 0 and y2 equal to -1. y1 equal to 0, y1 equal to 0 and y2 equal to -1. So -1 and 1, if you can see. Okay. If you can see, you'll find y1 equal to 0 and y2 equal to -1. y1 equal to 0 and y2 equal to -1 have -1 as common. Okay. So -1 and +1, -1 and +1. So x equal to -1 and y equal to +1 have 1/7 as probability. Okay. So the probability is 1/7. Okay. And then again, y1 equal to 1 and y2 equal to -1. y1 equal to 1, this one, and y2 equal to -1, nothing is common here. So it comes out to be 0. And at last, when y1 equal to 2 and y2 equal to -1, so y1 equal to 2 and y2 equal to -1, here it is 1, 1, it is -1, 1. So again, the probability is 0. Okay. In a similar manner, when y1 equal to -1, y2 equal to 0, y1 equal to -1. Okay, let me erase this so that it is easy to understand. Okay, so y1 equal to -1, y2 equal to 0. So y1 equal to -1, y2 equal to 0. It has -1, 0, -1, 0 as common. And the probability for x equal to -1, y equal to 0 is 1/7. So the probability is 1/7. Okay. Again, 0, 0. So the value is 0, 0. This one is 0. This one is 0. And the common portion is, if you see, it is here, 0, 0. So if you can see here, if you can see 0 and 0. So it comes out to be 2/7. Okay. So the probability value here is 2/7. And when it comes out to be minus y1 equal to 1 and y2 equal to 0. So y1 equal to 1 and y2 equal to 0, y1 equal to 1, y2 equal to 0. So it is 0, 1, 1, 0. So in 0, 1, 1, 0. So 1, 0 and 0, 1. So that means 0 and 1, this one, and 1 and 0, this one. So we need to add 1/7 plus 1/7, and this comes out to be 2/7 again. Okay. And in a similar manner, if you can use this, then it comes out to be here 0, 1, -1, 1, 0, 0, 0, and 1/7 here. Okay. So and if you sum this, you will find nothing but the summation is 1. Okay. So here we have constructed the joint distribution of y1, y2 random variable, which is associated with the discrete random variable x1, x2 in via this formula. Okay, via this relation, then we are able to find the joint probability mass function of y1, y2 random variable. Okay, so this is how we calculate the joint distribution, joint transformed distribution actually. Okay, when we have known distribution. Okay. Similar approach, we have also one more example. Okay. Is there any doubt? If then you can ask. Okay. Now suppose we have one more example. Let let the random variable x follows binomial distribution with the parameter n and p. Okay. Also, the random again the another random variable y follows the same distribution with parameter n and p, the binomial distribution. Okay. Now assume that these random variables are independent. Suppose assume these random variables are independent. Okay. Now we need to find the probability, the distribution of, like, find the distribution of x plus y. Okay. We need to find the distribution of x plus y when we are given x follows binomial distribution with parameter np and y also follows binomial distribution with parameter np. And these random variables are independent in nature. Then in that case, these are already discussed. Just we will have some recap. Okay, so here let, for example, let we have considered is a z random variable, which is summation of x plus y random variables. Okay, here if you know, since x follows binomial and y follows binomial, then the range of x is what? 0, 1, 2 up to n. And similarly, the range of y or the possible values of y are also like 0, 1, 2, n. Okay, so since z is defined as x plus y, so the possible values of z may is 0, 1, 2 up to 2n. Okay, so we have the range of z random variable, which is defined as x1 plus, sorry, x plus y. Okay, now we need to find the distribution of z. So this is like probability. Okay, we can replace the probability z by x plus y. Okay, since it is a joint distribution, and we can write here like probability, then x plus y is z. That means x equal to I, if we consider a dummy, x equal to I, then y equal to z minus I, so that x plus y equal to z only. Okay, now we are also given these random variables are independent in nature. So this implies this joint PDF, sorry, PDF, I mean PMF, this joint probability mass function is defined as like probability that x equal to I into probability that y equal to z minus I. Okay, since we know that when two random variables are independent, then their joint is equal to the product of their marginals. Okay, so we have written like this. Now we already know x. We know na, x follows binomial np and y follows binomial np. Okay, so we can write, okay, we can take summation over here, na, because we need to run for. So probability that x equal to I, the, if you know, also let me write, then probability that x equal is nothing but ncx e to the power x 1 minus p to the power n minus x. This is the form of binomial distribution. So we use this form here. So we take summation over I. Probability that x equal to I is NCX. Sorry, NCI is there only. NCI p to the power I and 1 minus p to the power n minus I. Also for probability that y equal to z minus I. So we need to write again NC z minus I p to the power z minus I 1 minus p to the power n minus z minus I. Okay, so this is the form. And when you see that there are many properties like NCI equal to NC n minus I. Okay, and p to the power I, p to the power z minus I, that comes together. Then it after solution, after simplifying, p to the power z comes there. So we can write it like this actually. Okay, I'm going to write the final version actually. Okay, so it is actually 2n Okay, 2n p to the power z and 1 minus p to the power 2n minus z. After simplifying, we will get this. Okay, and we know that z equal to 0, 1 up to 2n. So if you carefully look the form of this z distribution, you will find like it is nothing but the binomial distribution again with 2n and p parameter. So we can conclude thus here z, which is x plus y, is following a binomial distribution with n equal to 2n. Here the n parameter replaces by 2n and the p parameter is common. Okay. So we can like we see that here x1 is binomially distributed. Okay. Here x1 is binomially distributed and x is binomially distributed and y is also binomially distributed with same parameters n and p, and these random variables are independent. Then the z random variable, which is defined as the summation of the x plus y, okay, is also binomially distributed random variable with parameter 2n plus p. Okay, so this is how we find the transformed random variable with the help of the known random variable. Okay, again, even this can be true for this particular like property can also be held. Suppose if we have x random variable which follows np and we have another random variable y which follows binomial but not np but m and p. Here the probability of success is common. One parameter which is probability of success is common and the number of trials is not equal or not common. Then also x and y are independent. Then in that case, the transform variable z, which is x plus y, okay, this again follows binomial distribution with parameter n plus m and p. Okay, so when we have known distribution, okay, uh, like x for x and y random variable, then we can use the concept and find the transformed random, the distribution of the transformed random variable. Okay, and here in binomial case, the summation of binomially distributed random variable, which is independent as well, is nothing but again a binomial random variable. Okay, the similar case is observed for Poisson distribution. Like suppose if x follows Poisson lambda, okay, x follows Poisson distribution with lambda parameter, and y again follows Poisson distribution with suppose mu parameter. Okay, then z, which is defined as the summation of x plus y, is also follows Poisson distribution with parameter lambda plus mu. Okay, so this is one of the properties of the distribution of these kind of random variable, which is called reproducibility probability property. Sorry. Okay, let me write it as a reproductive property. So this property actually means if we have a sequence of random variables, let me write. Okay, if we have a sequence of random variables, and if we make a summation of few random variables, and if we take uh, and if we take a sum of few random variables, okay, and after taking those summation, and after it or after making the summation, okay, if we get the same distribution, we get the same distribution, then we conclude that the random variable have the reproductive property. Then we conclude that the random variable have the reproductive property. Okay, that means if we have a x1, x2 up to infinite, suppose like x1, x2, xn, a sequence of random variables, and suppose we have taken xi, I from 1 to n random variable, then if this z follow the same distribution that the x1 follows, that the x2 follows, then that kind of then that random variable is have a reproductive property. Okay, and this property can be seen for Poisson distribution that we have discussed here, binomial distribution that we have derived here. Okay, and some more distributions also like since binomial that we have already discussed. Okay, binomial distribution have reproductive property. Poisson distribution have reproductive property, and these are discrete case. Okay, and for continuous case, normal distribution also have the reproductive property. Just wait. Hello, I'm audible?
Yes, sir.
Okay, thank you. I'm not feeling well. Okay, now, so these kind of distributions have reproductive property. So we have its form, like its functional form, its transformed random variables distribution. Okay, now the same will apply for, we since up to this point we have discussed about discrete kind of random variables. Okay, now we will discuss about continuous, like in theorem form, like let x and y be a two-dimensional continuous random variable. Let x and y be a two-dimensional continuous type random variables. Okay, with joint PDF, we are given fxy. Okay, now suppose define z, which is function of xy as h1, and again w, which is h2, a functional form of x and y. Okay, then suppose we have two assumptions also. Okay, so assumption one is like we are able to solve these transform, like here these this expression can be like used as a transformation equation by using lowercase, like z equal to, suppose h of xy and h2 of x and y. Okay, so suppose these can be uniquely solved. Okay, solve this uniquely for x and y in terms of z and w. Okay, for example, the solution comes out to be like this, like x equal to g1 of z and w, and y equal to z2 of z and w. Okay, suppose we are able to uniquely solve this equation, and one more equation, the another assumption is like another equation, like the partial derivative, the like partial derivatives, like del x by del z, del x by del w, del y by del z, and del y by del w exist. Okay, and are continuous functions. Okay, so suppose we have xy two-dimensional continuous type random variable. Okay, and we need to find the distribution of transformed random variable z and w. Okay, which is a function of x and y only. Okay, and we have two assumptions, like if we are able to solve z and w, uniquely solve z and w. Okay, for in this format. Okay. And also the partial derivative of x and y with respect to z and w exist and are continuous function. If these two conditions satisfy, then in that case, the joint PDF of the transform variable z and w is defined as like, suppose z w is defined as like f x y. Here we need to write z. Z is not like here x is what? If you can see, we can write x equal to g1 of z and w. Okay, g1 of z and w and g2 of z and w, then multiplied by the Jacobian, the determinant of Jacobian actually, z and w. Then we can where like the Jacobian of z and w is defined as like this: del x by del z, del x by del w, del y by del z, and del y by del w. Okay, this must not be equal to 0 actually. Okay, so in that case, suppose these conditions satisfy, okay, then we are able to find the distribution of transform random variable z and w, okay, via this formula or this expression. Okay, so let's have one example to understand this formula. Okay, like suppose let xy be a two-dimensional random variables with joint PDF like fxy. Okay, this is known or this is given. It is defined as like one when the value of x lie within open interval 0 1, and the value of y should also lie within open interval 0 1 and 0 otherwise. Okay, so this is how the joint distribution of f x y random variables is defined. Okay, now we need to find the distribution of transform random variable. So let's define z, which is equal to x plus y, and w, which is equal to x minus y. There are different kinds of transform random variables. Here z is defined as x plus y and w is defined x minus y. Okay, so our aim is to find the joint distribution of like find the joint distribution of z and w. Okay, so using the above theorem, okay, our aim is to like first check whether the two assumptions are hold or not, and then if these two assumptions hold, and then we use the star expression to calculate the joint distribution of z and w. Okay, so okay, the first one is like here z equal to x plus y and w equal to x minus y. Then we write the transformation equation by using smaller lowercase like z equal to x plus y and w equal to x minus y. So if you add these two, then you will find x is nothing but z plus w by 2. Okay. And again, if you subtracting them, then you will find uh, y is z minus w by 2. Okay. So we are like able to uniquely solve this. Like the assumption one is hold actually. Assumption one is true here. Okay. So the first assumption is true. We are uniquely express x and y in terms of z and w. Now the second, we need to calculate the partial derivative. Okay. So here like x by del x by del z. So del x by del z is nothing but 1 by 2. Del x by del w is also 1 by 2. Again, del y by del z, it is also 1 by 2. And del y by del w, it is minus 1 by 2. Okay. Now the next step is to calculate the determinant. So determinants of z and w, which is it's 1 by 2, 1 by 2, 1 by 2, and minus 1 by 2. And if you solve this, you will find minus 1 by 2. Okay. Now, since the assumptions are satisfied, the next step is to use this star equation. Okay. This expression is used to calculate the joint. So f z w is, since it is 1, na, here it is like 1 and 0. Sorry. Since it is 1 and 0, so there is no variable of x and y. So directly we need to write like fx and y, g1 of zw, g2 of zw, and then Jacobian of zw. Okay. And also, this is the formula. Okay. We will put the formula. Also, we need range actually. Okay. We need range. So here you see that. Let me change the color. For range, like the range of x is 0 to 1, and x is nothing but z plus w by 2. Okay. Or you can write like 0 z plus w 2, and for y 0 z minus w 1 by 2, or you can write like 0 z minus w 2. Okay. So this is the range for the transformed random variable which satisfy z plus w less than 0 to 2, and z minus w is also lie within 0 to 2. Okay. So the final version is like 1 by 2 when the range satisfy z plus w by 2 and also z minus w by 2 and otherwise. Okay, so this is how we calculate the joint distribution of the transformed random variable z and w when we are given the distribution, the joint distribution of x and y random variable, Okay, I hope it is clear, na? Otherwise it comes out to be 0. If like since
Yes,
we are given, okay, is there any question?
no, sir.
Okay, okay, okay. Since now we have joint distribution, so we are able to calculate the marginal even. Okay, so these are already discussed in the lecture actually. I'm just writing to take some recap. So like if you are going to solve the marginal of z, you will find z, then you need to take the range for w only. Okay, f of z and w, and after solving, after simplifying, you will get either z or 2 minus z or 0. Z will occur when lie within 0 to 1, 1 to 2, or otherwise. Okay, you just solve these questions, you will find the same answer. Okay, and for w as well, take the range of z here, and this will comes out to be like w plus 1, 1 plus w when it the value of w lies within 0 to 1, minus 1 to 0, 1 minus w when it comes out to be 0 to 1 and 0 otherwise. Okay, so since what we have done here, actually, just take one more recap. We are given the joint, we are given x, y two-dimensional random variable. Okay, and defined like this. Okay, and we need to find the distribution of some transformed random variable. Here the transformed random variable is z and w, which is defined as x plus y and x minus y respectively. We need to find the joint distribution. So first we need to check whether this transformed random variable follows the above two assumptions. And we have we found out that like this follows these assumptions. Okay, so we can directly use the theorem that we have discussed above, and with the help of those theorem we are able to calculate the or find the joint PDF of z and w transform random variable, that is. Okay, and also since we are now transform joint distribution, then with the help of those joint PDF, we are able to evaluate the marginal PDF of random variables. Okay, here you see that actually directly here z and w are not independent random variable, because when we multiply the fz into fw, then we are not able to find the joint PDF of fzw. But here that the question is given like x y random variable. If you can find the marginal of x and marginal of y as well, and you will find that their x and y are independent random variable. So there is one more remark. Okay, that is, if we have different random variables that are joint, that are independent in nature, then when we define the transformed random variable, then it is not like sure, or it is not always true that those transformed random variables are also independent in nature. Okay, so here we can see here x and y are independent random variables, but the transformed random variables z and w are not independent. Okay, So it is not necessary that the transform random variable defined on independent random variable is independent as well. Okay. So there are some more like properties, some properties of like the same result. I'm just writing directly so that we can solve some questions as well. Suppose we are given x and y are two-dimensional random variables. Okay. And for consideration purpose, we have taken continuous. Okay. Continuous random variable. Okay. Then the first is like, suppose we have z, which is x plus y. Okay. The transformed random variable z, which is defined as x plus y. Then in that case, the PDF or the density function of z is defined as like integral the joint. Okay, that is already given. X and z minus x. Okay, so x plus y comes out to be z over here only, and dx. So by using this formula directly, we are able to calculate the the PDF of transformed random variable. Okay, again, suppose we have different transformed random variable, which is x minus y. Then in that case, this form is used to find the density of u, which is u transformed random variable, which is x minus y. Okay. In a similar manner, suppose we have product form random variables like v, which is defined as x into y. Okay. Then dx. Okay. And and if we have in division form, like w equal to x divided by y, then the density function of w is it is xw and x and product of x dx. Okay, these form or formula is directly used when we have different kind of, like we have bivariate random variable. Okay, like joint distribution, two-dimensional continuous distribution, and we need to find the distribution of transformed random variable, either x plus y or x minus y or x into y or x divided by y. Okay, so directly these formula can be used. Okay, now the next topic is ordered statistics. Okay, ordered statistics, like suppose we have n-dimensional random variable like x1, x2, xn. We have n-dimensional random variables, and from there we have considered n tuples. Okay, x1, x2 up to xn, n tuples are there. Okay, then we define like in this form. Suppose we arrange these n tuples in ordered form, in ascending order or descending order. So for example, we have considered like this. Okay, and these are arranged by the value of this magnitude only. Okay, so this is ordered variant form. Okay, where like x1 is nothing but minimum of x1, x2, xn. So when we use x and in base like in parentheses 1 or 2, then it is ordered variable. Okay. So it is the like second smallest value in x1, x2, xn. And in a similar manner, if we have written like xn, then that is maximum of x1, x2 up to xn. These maximum or minimum is defined via the magnitude or the value of the x1, x2 or xn random samples. Okay, so this is called like ordered statistics. We have different samples, we ordered them, okay, by their magnitude, we ordered them, so it is ordered statistics. It has its own like property and applications. Okay, and we have some formula, some direct formula to find the first order, second order, ith order or nth order statistics. Okay, the distribution of those statistics actually, that I can directly write as a theorem form. Okay, like the first one is like suppose the joint PDF of x1, x2 up to xn uh, can be defined like this. Okay, I'm just writing the uh, direct form. There are one actually assumptions. Okay, suppose we have x1, x2, xn random variables. Okay, and these are IID, independent and identically distributed random variables. Okay, then the first one is like the joint PDF of x1, x2, xn. Here, these are normal random variables only. Okay, and in the letter, I have written like in parentheses 1 and in parentheses 2 and n. So that is ordered form. Okay, when we write like in parentheses, then by default it is ordered format. Okay, so the joint PDF of x1, x2 up to xn is defined as uh, like f of x1, x2, xn. These are just notation actually. Okay, these are defined as like, since we are n samples, so there are n factorial possible ways to order them. So n factorial and the product I from 1 to n f of xi. Okay, here you can see that we have taken product because we have already assumed that it is IID, identically and independent and identically distributed. Okay, so x1 has the same distribution, x2 has the same distribution, all x1, x2, and xn have or same distribution. So we have considered n factorial and then product of f of xi at ith, and I taken from 1 to n. Okay, so the joint distribution, the ordered format, when we discuss about the order statistics, the joint PDF is calculated by this theorem, okay, or by this expression. Okay, also the we can also like calculate the marginal PDF or any or rth order random variable. Okay, so like the marginal PDF of XR, that is rth order random variable. Okay, so okay, let me write it in general format. So XR. Okay, so this can be like calculated by this formula. It is n factorial. It is r minus 1 factorial. It is n minus r factorial, and then fx of xr to the power r minus 1 minus fx of xr to the power n minus r into fx of xr. Okay, so this is how we calculate the marginal PDF of the rth order statistics and the joint PDF of the rth order statistics by using second star expression and double star expression and single star expression. Okay, directly this formula can be used to calculate the rth order statistics or joint statistics of order statistics. Okay, now okay, we have one example here. Suppose let x follows exponential lambda, okay, and y also follows exponential lambda distribution. Okay, also assume x and y are independent. Okay, actually these are IID because it is independent. X and y are independent in nature and have the same parameter lambda. So these are independent. Okay, sorry. It is actually mu, not lambda. Okay, so it is independent and have the same distribution. Okay, exponential distribution. Now we need to find the distribution of minimum of xy. Okay, so we need to find the distribution of minimum of xy. So let's see how to solve this. For example, let we have considered the transformed variable z as minimum of xy. So now we need to find the distribution of z. Okay, so for z is greater than 0. Okay, for z is greater than 0 because here x and y are independent random variable, which is exponential. Okay, and exponential distribution has support greater than 0. So the minimum of x and y have also either is greater than 0. Okay, so for z is greater than 0, we need to write the probability that z equal to z. This is defined as probability that z can be replaced by minimum of xy greater than z. Okay, so minimum of xy is greater than z. That means what? Since its minimum is greater than z, so this means x is greater than z and y is also greater than z because the minimum is greater than z. That means both are also greater than z. Okay, and then since these x and y are independent in nature, so we can write like this. Na? The joint distribution can be written as a product of marginal. So x is greater than z and probability that y is greater than z. Okay, so probability that z is greater than z is defined as probability that x is greater than z into probability that y is greater than z. Okay, now since x follows exponential lambda, for example, then fx is lambda e to the power minus lambda x, and capital Fx, which is defined as probability that x is less than or equal to x, is 1 minus e to the power minus lambda x. These are already discussed in fourth week actually. I'm just writing. Okay. And probability that x is greater than x is defined as e to the power minus lambda x. Okay. These are already discussed actually. Okay. So we put this value. So we can write probability that z is greater than z is x is greater than z and y is greater than z. So this implies e to the power minus lambda z into e to the power minus mu z, which is e to the power minus of lambda plus mu z. Okay. So from here, like z, okay, and then we have calculated this value, na? Then probability that z is less than or equal to z is defined as 1 minus e to the power minus of lambda plus mu z when z is greater than 0 or 0 otherwise. Okay, so we are able to calculate the distribution of z random variable, which is defined as minimum of xy. So here, if you see, you can find that like z, which is minimum of x and y, also follows exponential distribution with parameter lambda plus mu. Okay, so that means here x is an exponential distribution, y is also exponential distribution. We define a transformed random variable, which is minimum of x and y, and that also follows the exponential distribution with parameter lambda plus mu. Okay, there is one more topic, that is conditional distribution. Okay, so conditional distribution, like we have discussed about conditional probability. You people may remember the conditional probability, like since A given B is what? Probability of A intersection B upon probability of B. In a similar manner, we can define for discrete and for continuous case both. Okay, like for discrete, agar, like for discrete case, so probability that x given y equal to y. Here, the given condition y equal to small y is treated as like constant. Okay, so it is like probability that x equal to x, y equal to y, and y equal to y for discrete case. Okay, and suppose if we are discuss about continuous case, in that case, the fx given y equal to y, then it is provided like fy is greater than 0, and here also y equal to small y is greater than 0, so that it is a valid PDF. Okay, so these are the how we calculate the conditional distribution. Okay, when we are given a joint distribution. Okay, then joint and marginal, the help of those joint and marginal, we can able to calculate the conditional distribution. Okay, so this is it. Like there are random samples is also there, random sums is also there, actually not sample. Random sum is like suppose we have x1 x2, like let we have x1 x2 xn be a sequence of random variable. A sequence of random variables. So we define Sn, which is defined as nothing but summation x1 plus x2 plus xn. Okay. Then this Sn is called the random sum. Okay. Where n has like a discrete type positive integer random variables, then this Sn, where n is like discrete type positive integer random variables, then in that case, this Sn is defined as random sum. It's called as like random sum. Okay, that means when we have different sequence of random variables, then up to any finite values of like those random sequence, random variables, then that sum is called random sum. Okay, so these are the topics like we have discussed in the 6th week. Okay, we can solve some numericals based on this. Like if any doubt, you people may ask. Okay, I'm just taking because there are like many concepts or many topics is there that like I'm not able to discuss in 2 hours, so I'm just writing some words. Okay, so we will now going to solve some questions related to these topics. Like the first question is, suppose let x and y be two continuous random variable. Okay, with joint PDF is given by like this. Okay, we need to find the marginal PDF of x. We need to find the marginal PDF of x. Find marginal PDF of x. Okay, so we need to find like this. It is simple. We are given joint and we need to calculate marginal. So that we have already like discussed. Okay, so simple. Suppose the marginal is defined like this. It is integral taking the range of the y, which is from 0 to 1 and 2x. Okay, so it is like 2x are taken as common because that are treated as random as constant, and y 0 to 1, and it comes out to be, okay, wait, I think I've written something wrong here. Okay, 2x. Okay, yes, sorry. Here the range of y is 0 to x actually. Okay, so here also it's 0 to x. Okay, so here again 0 to x. So it is 2x and x minus 0. So the marginal of x is like 2x squared, or x lies between 0 to 1. Okay. So we can calculate the marginal of x. Now with the help of this marginal of x, we can calculate the other statistical characteristics. Like suppose if we want to calculate the expectation of x, then it is defined as like integral over x from 0 to 1, x into fx dx, which is 0 to 1 to x square into x dx, which is like x cube dx, 0 to 1. So it is twice, it's 1 by 4 minus 0, it comes out to be 1 by 2. Okay, and in a similar manner, you can calculate the variance and other MGF and all the statistical characteristics since we have PDF. Okay, so this is how we use. Now the next question will be like Okay, we have one more question, a discrete type now. The question is, let x and y be a discrete random variable. Let x and y be discrete random variables, okay, with support like defined like this: rxy equals 1 0 2 0 1 1 and 1 2. Okay, and joint PDF, in the joint PDF is given like this: probability that xy, it's 1 by 4 when x equals 1 and y equals 0, again 1 by 4 when x equals 2, y equals 0, 1 by 4, x equals 1, y equals 1, and 1 by 4 when x equals 1, y equals 2, and 0 otherwise. This is how the joint probability mass function is defined. Now we need to find, yes, sorry, find the conditional distribution, okay, and then like conditional probability x equal to 1 given y equal to 0. Okay, fine. We need to find this. We are given the joint distribution, joint probability mass function, and we need to calculate the conditional probability of x1 equal to 1 given y equal to 0. So let's start the same basic formula. Since probability of A given B is like probability of A intersection B upon probability of B greater than 0. Okay, this is the case. So here probability of x equal to 1 given y equal to 0 is like probability of x equal to 1, y equal to 0, and divided by probability that y equal to 0. So probability that x equal to 1 and y equal to 0, that is in numerator, is already here. Na? Like x equal to 1, y equal to 0 is there. So the numerator value is 1 by 4 actually. That is directly taken from the joint probability mass function table. Okay, now we need to calculate the denominator part, that is probability that y equal to 0. Again, probability that y equal to 0 is taken from, we have taken the range of x, probability xy, x equal to x, y equal to y. Okay, from joint we need to calculate marginal. Then marginal is taken x, the range of x is like 1 and 2. Okay, so the range of x is 1 and 2. Here actually we need to, this is a general form actually, na? So we can write here, because y equal to 0, we need to find the only y equal to 0 only. Okay, then for y equal to 0, if you see here, for y equal to 0, we have only two format. Okay, so for y equal to 0, we have x is equal to 1 to 2. That means probability that x equal to 1, y equal to 0, plus probability that x equal to 2, y equal to 0. If you can see from the joint PMF, y equal to 0, x is equal to 1 by 4 is there. And for y equal to 0, x equal to 2, 1 by 4 is there. So that means it is 1 by 4 plus 1 by 4. That is 1 by 2. So probability that y equal to 0 is 1 by 2. Okay. Now we need to calculate probability that x equal to 1 given y equal to 0. That is probability that x equal to 1, y equal to 0 divided by probability that y equal to 0. Now probability that x equal to 1, y equal to 0 is 1 by 4 here that we have already discussed. X is equal to 1, y equal to 4 is y equal to 0 is 1 by 4. So the numerator part is 1 by 4 and the denominator that we have already calculated is 1 by 2. So after solving, you will get 1 by 2. So probability that x equal to 1 given y equal to 0 is 1 by 2. Okay, just simple equation, simple procedure. Okay, the conditional is defined as joint divided by marginal. Our aim is to first calculate the marginal and then putting those values in this expression, we are able to calculate the conditional probability. Okay, like in a similar manner, suppose suppose we can ask like this, like find the probability that x equal to 2 given y equal to 0, then it is nothing but x equal to 2, y equal to 0, probability that y equal to 0. So x is equal to 2 is also like 1 by 4, I think. X is equal to 2, y equal to 0 is also 1 by 4. So this implies it is 1 by 4, 1 by 2. It comes out to be 1 by 2. You can take the value of y at 1 if you want. Then we need to first calculate the marginal distribution of y at y equal to 1. And after that, we can use those values in denominator and solve the conditional probability. Okay. Now, one more question. Like we are given a discrete random, we are given a bivariate two-dimensional random variable. So the joint distribution of two-dimensional random variable is given 2x e to the power minus of x 2 plus y. Okay, for x and y greater than 0. Okay, we need to find the PDF of x. Again, we are given the joint, we need to find the marginal actually. So this is again like simple integral, taking the value of y, which is 0 to infinity, 2x e to the power minus of x 2 plus y dy. Simple. Just try to solve with by yourself even. Okay, let's see. Now, since x is taken as common, so 2x is taken as common, e to the power 2x into e to the power minus xy. So into e to the power minus 2x is also taken as common. So it is actually 0 to infinity e to the power minus xy dy. Okay, e to the power minus xy dy. And if you people know, since here x is like taken as a constant, treated as constant. So if you know the integral over 0 to infinity e to the power minus ax dx is nothing but 1 by x. Okay, sorry, 1 by a, not 1 by x. 1 by a, where a is greater than 0. This is already known formula. Okay, known. So using this concept, we can directly calculate 2x e to the power minus 2x into 1 by x. Okay, so our marginal is like 2 e to the power minus 2x, or x is greater than or greater than 0, I think. Okay, x is greater than 0. Okay, now the next question. Like the question is, let the joint PDF of a random variable x and y is given by, here given, let the joint PDF of random variables x and y is given by, it is given by like 8xy when 0 x y 1 and 0 otherwise. Okay, we need to find expected value of y given x equal to x. Okay, so since we need to find the conditional expectations now, so since the expected value is defined as integral over x into fx, so our aim is to first calculate the conditional distribution. Okay, once we have conditional distribution, then we can solve the expected value. Okay, so like we need to first find the conditional y given x equal to x, and this is how this is defined, like the joint divided by the marginal. Okay, so now we have joint distribution, but we don't have the marginal of x. So first we need to calculate the marginal of x. Then with the help of those marginal of x and joint of xy, we are able to calculate the conditional of y given x. And then with the help of those y given x, we are able to calculate the expected value of y given x. Okay, so let's start. So fx of x will be like 8xy. Okay, so it is y 8xy dy, and the range of y is taken from x to 1 actually. If you can see here, y is lies between x to 1. So x to 1, 8x is considered as common. So y square by 2 is there. X to 1, 8x, 1 by 2 minus x square by 2. So just simplify 4x 1 minus x square, or x lies between 0 to x. So this is the marginal distribution of x. Now, since we have marginal distribution, so we have y given x, which is joint divided by marginal, which is 8xy, and 4x 1 minus x square is there. So just simplifying, these expressions, we will get actually 8x will be cancelled out and it's 2y divided by 1 by x square. Okay, for 0 x y. Okay, because for any particular value of x, we have a PDF of y given x equal to 2. Suppose y given x is equal to 0.3 because x and y both lie within 0 to 1. Okay, so this is the conditional distribution of y given x. Now, the next is expectation of y given x. So the expectation is defined as like integral. It's a function of y only. X is treated as constant, but since we are dealing with x is equal to small x, then the same formula is used. So y into f of y given x, y given x dy. So it is y into 2y divided by 1 minus x square, and the range of y is like range of y here is x to 1, x to 1 dy. Okay, so it is like 2 upon 1 minus x square taken outside from the integration 0 to 1, it's y square dy. Okay, so it is 2 upon 1 minus x square is there. It is y cube upon 3 x to 1. So it is 2 upon 1 minus x square. It is 1 by 3 minus x cube by 3. So just simplifying, it's 2 by 3 is there. 1 minus x cube upon 1 minus x square. This is nothing but expected value of y given x. Okay. Now suppose at suppose x equal to 0.5. For example, we have considered x equal to 0.5. Then expected value of y given x equal to 0.5 is nothing but 2 by 3 into 1 minus 0.5 cube 1 minus 0.5 square. It's a calculation that I have not done. Okay, so it's 2 by 3. It's 1 minus 0.125 and 1 minus 0.25. Okay, and it's 2 by 3. So it is come 0.875 and it is 0.75. So just you can solve this. Okay, I don't have like the solution for this. So this is what the answer. Okay, so you can simplify this. Okay, so this is how we calculate the conditional. Okay, let's discuss one more question. Actually, there is a question here. The question is, let x and y be IID exponential lambda. Let x and y be IID distributed with exponential lambda distribution. Let z equal to maximum of xy. Okay. Then check whether the distribution of Z and x plus half of y are same or not. Okay, so just give it a try. We need to check whether the distribution of Z and the distribution of x plus half of y have the same distribution or not. Okay. Okay, let's start. Then the first start with the CDF of Z. Let CDF of Z is like written like this. Define as probability that Z is less than or equal to Z. Okay. And it is defined as probability that Z is defined as maximum of XY. So it is maximum of XY less than or equal to Z. Here you can see that the maximum of X and Y is less than Z. This implies X and Y both are less than Z. So we can write like this: probability that X is less than or equal to Z, Y is less than or equal to Z. Okay. Here it is also given X and Y are IID, independent and identically distributed. So this implies the joint can be represented as a product of marginal. So this means probability that X is less than or equal to Z into probability Y is less than or equal to Z. Okay. And then probability that X is less than or equal to Z, Y is less than or equal to Z, and X and Y both follows exponential lambda here. Both follows exponential lambda. Okay. So this is actually 1 minus e to the power minus lambda z into 1 minus e to the power minus lambda z, because the CDF of exponential lambda is this. Na? So both are identical as well. So fz of z is nothing but 1 minus e to the power minus lambda z whole square. Z is greater than 0. Okay. So the CDF of z is exponential lambda. Okay. Now we need to find x plus half of y, the CDF of x plus half of y, or the distribution of x plus half of y. So let w equal to x plus half of y. Okay. Since x and y are like since x and y are IIDs. Okay. So the joint of x and y is the joint distribution of x and y is like lambda e to the power minus lambda x, lambda e to the power minus lambda y. Okay. We can simplify, but let's remove, take it like this. Okay. Now we need to find probability. We need to find FW. Okay. That is CDF of W. So which is defined as probability that W is less than or equal to W. Okay. Now W is what? Probability that X plus half of Y is less than or equal to W. Okay. We can write like this. No? Now we need to integrate it over this situation or this condition satisfied. Okay, so this implies we integrate over all values of x and y like that satisfy this condition x plus half of y is less than w. So this implies x plus half of y is less than or equal to w. This implies like y equals twice of w minus x for x lies between 0 to w. Here, the value of x lies between 0 to w because here y and x both are exponentially distributed. Okay, so y or w minus x should also be positive, na? So that y is always greater than 0. So the maximum value of x is less than or less than w just. Okay, so x has range 0 to w and y has range twice of uh, w minus x. Okay, and that's also from 0 to there. Now, okay, this is up to this point. Now let's start. Probability that w is less than or equal to w. So suppose we have taken here y twice of w minus x and 0 to w. Okay, so PDF lambda e to the power minus lambda x lambda e to the power minus lambda y dy dx because I have considered the y first, the range of y I have considered it first. Okay, so this can also be written like this. Just a simple calculation. Okay, we need to just simplify step by step to find the PDF of w or the distribution of w. So it is 0 to w. Okay, and then y is there, then the x term can be like taken outside. Sorry. So lambda square e to the power minus lambda x is there, e to the power minus lambda y dy is there, and then dx is there. Okay, like we can take this. This is 0 to twice of w minus x. Okay, now just integrate the parenthesis part first. So it is lambda square 0 to w e to the power minus lambda x. Now the integration of e to the power minus lambda x is e to the power minus, sorry, lambda y is e to the power minus lambda y upon lambda or minus lambda actually 0 to twice of omega minus x dx. Okay, now we need to simplify this actually. Okay, so let me simplify this. It's lambda square integral over this e to the power minus lambda x and then put the value 0 because minus is there. So we have considered 0, then it comes out to be actually lambda maybe cancel out if you can see like 1 minus e to the power minus lambda into twice of w minus x whole divided by lambda dx. We're just putting the values actually. Now lambda is taken as outside from the integral. So lambda is square and divided by lambda is comes out to be lambda 0 to w e to the power minus this. And it is nothing but 1 minus e to the power minus 2 lambda omega minus, sorry, w minus x dx. Okay. Now, if you can see, we can parts it. Na? Lambda e to the power minus lambda x dx minus lambda e to the power minus lambda x into e to the power minus 2 lambda w minus x dx. Okay, just multiply e to the power minus lambda x and open the parenthesis. We can write it in this part form. Now, again, lambda is here, e to the power minus lambda x. It is 0 to w actually. Everyone is 0 to w now. Upon minus lambda, 0 to w, minus lambda is there. Okay, we can simplify this, multiply this e to the power minus lambda x minus e to the power minus 2 lambda w minus x. Then e to the power minus 2 lambda w is taken as common actually. Sorry, taken outside from the integral actually. E to the power minus 2 lambda w is taken outside. Then 0 to w e to the power plus lambda x dx is there. Okay, and the first part is like simplified and comes out to be like 1 minus e to the power minus lambda w, minus second part is like e to the lambda e to the power minus 2 lambda w, and e to the power minus lambda x after e to the power lambda x on lambda 0 to w. Then it is 1 minus e to the power minus lambda w minus lambda e to the power minus 2 lambda w, and it's
1 by lambda. E
yes,
to
yes,
the power
yes,
lambda upon
yes,
lambda.
yes, it is lambda. Okay, okay. Now lambda, okay, so it comes out to be like e to the power lambda w minus 1 divided by lambda. Okay, so 1 minus e to the power minus lambda w is here, minus lambda will be cancelled out, e to the power minus 2 lambda w, and it is here e to the power lambda w minus 1. Okay, so e to the power minus 2 lambda w is there. So 1 minus e to the power, just we need to like decorate it so that we have take some common. So e to the power minus lambda w into e to the power minus lambda w, 1 e to the power minus lambda w, and e to the power plus lambda w comes out to be 1 minus e to the power minus lambda w. Is it okay up to this point? How it comes? Like e to the
Yes,
power minus 2, okay, e to the power minus 2 lambda w and be written as e to the power minus lambda w into e to the power minus lambda w. 1 e to the power minus lambda w is multiplied in the parenthesis. Then this converted into this form. Now it is seen that now we have taken 1 minus e to the power minus lambda w is taken as common. Then it's 1 minus e to the power minus lambda w. Okay. And then we can find f is nothing but 1 minus e to the power minus lambda w whole square for w is greater than 0. So if you see here, fw have 1 minus e to the power minus lambda w whole square, and fz. Fz also has the, okay, fz also has the 1 minus e to the power minus lambda z whole square. Both have the same distribution. So yes, here z, which is equal to maximum of xy, and w, which is equal to half x plus half of y, have the same distributions. Okay, so this is the question actually. So we have calculated and we have found that both have the same distribution. Okay, so this is it actually. If you have any doubt, you people may ask. Okay, if you don't have any doubt, then I think we should close our session here. Okay, is there
okay.
any doubt?
Thank you, sir. No, sir.
Okay, thank you. Let me
Thank you.
stop the recording first.